If you want to find the area underneath a curve, the process is usually quite simple. You do the integral of the function with respect to x. Okay, seems simple enough, but what if your function was not y equals f of x, but rather it was something defined parametrically, maybe in terms of t, maybe in terms of theta. So x is equal to g of t, some function of t, and y is equal to some function h of t. Well, can we still integrate it? Good news is we can. We know what y is, because it's equal to this function h of t. dx though, that's not really going to happen because dx and t do not match up. Well, it's fine. We do a little trick. We divide by t and we times by t. And now hopefully you'll see that dx dt is the derivative of the x bit, which is just, in this case, g dash. Everything's in terms of t, we're all happy. That's at least the theory. Let's put it into practice so you can understand how to actually use this formula. Well, let's start off with a rather pointless example. X equals t, y equals t. This represents the line y is equal to x. Let's say we wanted to find the area underneath the line from 0 to 3. We probably wouldn't even integrate, but we could. We'd just use the area of the triangle here, being 1/2 times by 3 times by 3, or 9/2. But let's do it parametrically, because we can. Why not? The integral should be y dx. That's the classic integral. The limits are 0 to 3. What's y? Y is t. Dx. Can't really do much with that, so we turn it into dx dt dt. Timesing and dividing by the same thing. We're not going to harm anyone by doing that. dx dt, is that not just the derivative of x? What's the derivative of x with respect to t? It's just 1. What about the limits? These original limits are xy limits. But this final integral is in terms of t. So what we have to make sure is, when x is 0, what's the value of t? T is 0. When x is 3, what's the value of t? Okay, it's still 3, but you get the idea, it might change. Let's integrate this now. This is quite a nice integral, t squared over 2 from 0 to 3, which is, oh, look at that, 9/2. We get the same answer. You're not going to be asked to integrate something like that parametrically, but it's a good check to see that this formula does in fact work. Let's do another check for no other reason than we can. X equals sine t, y equals cos t. I won't go through the reasoning, but make sure to review your parametrics if you don't know, but this represents a circle where it borders on 1 and -1 here and here. What I'm going to do is I'm going to find the area of this bit here. We could find that by doing 1/4 of the area of the circle, which is 1/4 pi r squared, pi over 4. Let's now do it parametrically, see if we get the same answer. So we're integrating from x equals 0 to 1 of y dx. Again, that's the classic definition of the integral. But we don't really want that because everything's in terms of t. So let's replace y with cos of t because that's its definition. Let's divide and times by dt because that makes everything into t's. dx dt is the derivative of x, which is cos t. And now we think about changing the limits. When x is 0, what does that mean t will be? Well, if we do inverse sine of 0, we get 0. I'm sure I said these limits shouldn't always be the same. When x equals 1, the inverse sine, okay, that's going to be pi over 2. So not always the same. Now it's a case of integrating this. So this is the integral of cos squared from 0 to pi over 2. If you're not confident on how to solve this integral, visit my trigonometric integration video. I'll show you how to do it anyway, just briefly. We want to use the cos double angle formula. Whenever it's a cos squared or a sine squared, always the double angle formula is the way to go. So cos 2t is 2 cos squared t minus 1, which if we rearrange to get cos squared on its own, we'll get this 1/2 of cos 2t plus 1/2, which we can then put back into the original integral to give us the integral of 1/2 cos 2t plus 1/2 dt from 0 to pi over 2. Let me scroll down. We can now integrate this because cos is something we can integrate. If we divide by the 2, we're going to get 1/4 sine 2t. And the integral of any constant is that constant times by t. Do you remember you're in t land now? X's are out the window. This is from 0 to pi over 2. If I put pi over 2 in here, that's going to be 0. And then this is going to be half of pi over 2. That seems promising. And if I put 0 in here, I get 0 plus 0, which is 0. And we get pi over 4, which is exactly what we wanted, which seems very, very good. This check shows us that the formula works, and now we can use it for more complicated examples if that wasn't complicated enough. Okay, here's our first proper example. This time we've got x equals tan t and y equals sine 2t defined on this range, and I've got a little diagram here to help us out. We want to be looking for the area between x equals 1 and x equals root 3 underneath the curve, which is just here. Let's use that formula. This formula is not given, so I'd highly recommend memorizing it. Although if you know the definition of an integral, there's really not much change. Times by dt, divide by dt. Y is first, and that is sine 2t, according to the question. Next is dx dt. Do you remember the derivative of tan t? That's right, it's sec squared. That is in the formula book, but I think it's a good one to memorize. And then quickly just thinking about the limits. If x is equal to 1, then 1 is equal to tan of t. So t is equal to pi by 4. And if x is equal to root 3, then root 3 is equal to tan t, or whatever that says. So t is equal to pi by 3. So we can put these limits here and here. Just a word of caution, sometimes the limits change direction, and the smaller limit is at the top and the bigger limit is at the bottom. Match up the value of x to the value of t and don't change it just because it feels right. Now we want to use our definition of sine 2t, which is 2 sine t cos t times by sec squared t dt. Too many t's, if you ask me. What's the definition of sec squared? It's 1 over cos squared, which means we can write this as 2 sine t cos t over cos squared t dt. And one of these coses, boop, boop, is going to disappear from the numerator and the denominator. So who'd thunk it? We've got tan, or 2 tan dt. To integrate tan, we can either use the formula book or we can use the ln rule, which is very, very helpful. So the answer is going to be 2 ln sec t, and then the limits are still pi over 4 to pi over 3. Ooh, it's now a case of just subbing in. So we've got to do 2 ln of sec pi over 3 minus 2 ln of sec pi over 4. I can now turn that into cos by doing this. Sec is cos to the power of minus 1, so using the laws of the natural logarithm and bringing up the power of minus 1 and then bringing it down to the front. Similarly, I can turn that into a cos. Power of minus 1 is floating around, so I'm bringing it to the front. And if we continue, cos of pi over 3 is a half, like this. and cos of pi over 4 is 1 over root 2. And I know I just brought those negative numbers out, but I'm actually going to put them straight back in, and I'm going to do the reciprocal of these two insides, like this, which we can then write as 2 lots of ln 2 over root 2, and 2 over root 2 is equal to root 2, which is 2 to the power of a half, which you can bring down to the front times by half, and we get ln 2. Who knew that a parametric integration could give such a nice answer? Well, I did, because I made the question. In this next example, we're going to be integrating underneath the curve with these parametric equations, where t is any real number. And we're going to do it from 1 to e. Let's see what we get. So this is what we usually want to do, but we can't. So we divide by dt, and we times by dt, and then suddenly everything seems a bit clearer. We know what y is. That's 1 over 1 plus e to the t, and dx dt is the derivative of x, which in this case is 2 e to the 2t. Pop our dt on the end. How about the limits? When x is equal to 1, that means e to the 2t is equal to 1, which means that 2t is equal to 0, which means that t is equal to 0. When x is equal to e to the 2t is equal to e, 2t is equal to 1, and then t is equal to a half. So our limits are 0 to a half. If I now write this all as one fraction, it will be 2e to the 2t over 1 plus e to the t dt from 0 to a half. If you're not quite sure of the method, go back to my substitution video. Maybe that gives you a hint. I'm going to use a substitution u equals 1 plus e to the t. I'll do this method quite quickly. Again, revisit the video if you're unsure. This video is not really about substitution, but as a quick reminder, we make u the substitution, we do the derivative, we sub it in, we see what cancels out, we change the limits if we want to, but we don't have to, and then in my case, because I changed the limits, I'm going to sub the new limits into the integral answer. And we get an answer that is nowhere near as nice as the last one. I don't know who writes these questions, but there we go. 2e to the half minus 2 ln 1 plus e to the half plus 2 ln 2 minus 2. And for this last example, we're trying to find the area underneath the curve between 0 and 1. I'll first pop down the formula, and then we'll try and fill in the values. We know what y is, it's t ln t. Do we know what dx dt is? Well, the derivative of ln t is 1 over t. Now let's think about the limits. When x is 0, ln t is 0, and if the natural log is 0, it means that t is 1. If x is 1, then ln t is 1, so t is equal to e. So the limits are 1 to e. Now to integrate this, you'll notice that the t's cancel out, which means that if we want to integrate this, we need to know how to integrate ln t. This is a by parts. It doesn't look like one, but we need to add times by 1 at the end to turn it into a by parts. If you're not as familiar with that method, visit my by parts video. I'm going to let u equal ln t and find the derivative. I'm going to let the derivative of v be 1 and integrate it. Almost put x there. Then I'm going to do these two, t ln t minus the integral of these bottom two, t times 1 over t is 1, like this. To be proper, I probably should put the limits around here, but I'm going to be lazy. The integral of 1 is simply t. Now I'll put the limits in. And let's see what we're going to get. We're going to get e log e minus e minus 1 log 1 minus 1. Looks a bit like the modulus of just ln without an x, but that's 1 ln 1. That's fine. ln 1 is 0, so that's going to disappear. ln e is 1, so that's going to disappear. And we're going to get left with e minus e plus 1 which is 1. That's even nicer than the first answer, and I didn't even see that one coming. The last thing I want to mention about the limits when using parametric integration is if your limits feel like this should be the other way around, say you integrate from t equals 0 to t equals minus 3, whatever this is inside, there is a way to swap it round, and that's simply by timesing the integral by minus 1. Sometimes questions are show that, so you need to actually show this step specifically, times everything by minus 1, and you can swap those limits around. Well, there you have it. Now you know how to integrate parametrically. If you want some extra practice, try these 2 extra questions. And as always, don't forget, +C.